Welcome everybody. I'm Sergio Rey. I'm going to give a talk on introducing people to PySAL and a little bit of a story about the history and its evolution. For those of you who don't know me, I'm a professor at San Diego State, professor of geography. Before that, I was professor of public policy at UC Riverside. Before that, I was at Arizona State University, and I started my career at San Diego State a long time ago, so it's wonderful to be back home. I returned in 2002. My research interests are in GI science, geographic information science, spatio-temporal data analysis with substantive interest in the spatial social sciences, primarily studying disparities, spatial inequality, segregation dynamics, these types of issues. And because of my exposure to this and the SciPy community, I became an evangelist for open science inside my home discipline, inside the spatial social sciences. On the right, there are some projects since 2000. The Ritter Grant was an investment to build scalable segregation measures for sociologists and economists and geographers. The NIH project was with psychologists trying to disentangle the effects of neighborhood context on cognitive aging and decline. This is just to give you an idea of the breadth of the kind of spatial data in the social sciences, kinds of questions people are interested in. I'll illustrate some of these later on, so I don't want to belabor this point. At SDSU, I run the Center for Open Geographical Sciences, so the open part is critical because I've been trying to push this on my colleagues my whole career, essentially, and I thought rather than just another lab that had a generic name, you need an acronym, so COGS it is. These are the kinds of problems I work on personally, and in doing this, PySAL became scratching my own itch way back in the day. So for example, looking at the impact of the legacy of things like redlining, what is a spatial signature in terms of the loss of wealth for certain communities because of historical policies in the 1930s. Looking at place mobility, which has to do with, do the poor places in a country, say in Mexico, the municipios, do they remain poor, or are there actually dynamics in how they move up or down the income distribution? And what is the role of space and spatial context in that? I'll talk about the school neighborhood nexus project a little bit later, and issues of intersectionality. We think about this from an individual perspective. It's one thing to be a poor African-American woman, but where you're embedded in geographical space, you can think about the same kind of issues. Do we have poor neighborhoods that are also of a certain ethnic and racial composition, and how do those two factors influence how places may or may not change over time? So I'm a geographer by training, and I don't have to convince my colleagues that location matters, but it does. However, if you think about the social sciences, where I work in, up until the last century, space was pretty much relegated to being irrelevant. So the common models in the IID world, where you have random sampling, assume away a lot of the features of the world that we actually encounter when you work with social and spatial processes. So they ignore two fundamental spatial realities, that is spatial dependence. You are your neighbor's neighbor, and you both influence each other in different contexts. That needs to be taken into account in the modeling process. And then the notion of a global model that holds everywhere is pretty much a stretch in the social sciences. So it's very different from the physical processes that we're modeling. There's a difference between the truly hard, truly difficult sciences like climatology, physics, and the truly hard science, difficult sciences, namely the ones that deal with people. So we have one law in geography. It's Waldo Tobler, the late cartographer from San Diego State, from UCSB, that everything is related to everything else. That's the first law of ecology. But the nearer things are, that relationship tends to be increased. So as I said, I have a long-term interest in spatial disparities, and this is what got me into working with Python and these tools. This is a map of the US counties in 1989. That's the median family income, quintile map. And in this literature, there were basically two sets of scholars studying this. There was the geographers, economic geographers, who would look at the spatial structure of these maps and ask, are they random or not? And it's pretty clear visually that they're not. However, visual inspection can be challenging because these polygons are not consistently sized remote sensing pixels. They're all different shapes, all different sizes, and our eyes are drawn to those large polygons. So San Bernardino County up the road a little bit here, is larger than the entire state of Maryland, right? But from a statistical perspective, if you ignore space, each one of these units counts the same amount. However, when you build spatial context back in, that's not necessarily the case. So here's the way the two different disciplines. On the right, that would be the way the economists would study this question of divergence and convergence. What's happening to the gap between the wealthiest and the richest and the poorest counties, in this case, in the US over time. So they would study how the distribution evolves over time. Geographers look at that map that we just saw. But this process is a dynamic one. So you're really interested in both, not just how the attribute distribution changes, but also the spatial distribution. And it's clear that the traditional measures that are used, the traditional analytical devices, miss the spatial signature. So the density could be the same for an infinite number of maps, basically. So what we've been trying to do, me and my colleagues, is to develop spatially explicit analytics that capture the spatial signature in these processes. So on the top right, that's called a Moran scatter plot. I'll say a lot more about it later on, but essentially it's the analog to a temporal lag, but now with taking in spatial context into account. So the y-axis is the spatial neighbors of a given county, and you're asking, is there a correlation essentially in space between this attribute? And yes, there is. Okay. When the social scientists started grappling with space, there was a pushback from some of the time series modelers say, well, we know how to handle autocorrelation. We exploit it all the time to do better forecasting. However, temporal autocorrelation is a very different animal from spatial autocorrelation. In time, the arrow goes forward, right? The past influences the future. Future doesn't influence the past in most models. There's some rational expectation models where you could argue that's not true. And you have one first-order neighbor in time, whereas in space, the interactions are simultaneous, particularly if we aggregate over time. And you have multiple neighbors. So it's a much more complex type of dependence. So spatial data science, which is what we've been doing all the time, we just now call it spatial data science, is trying to build in the spatial structure into these social science models. We're trying to analyze patterns, discover the unexpected, predict outcomes, and build models of the processes that we think are responsible for the way the world is. And this is where PySAL came from, so the Python Spatial Analysis Library. A little bit of history where this comes from. Back in the early 2000s, there was a large NSF project to build technologies for the social sciences to introduce space into the analytical toolkit. So my colleague Luke Anslin, who's at the University of Chicago at the time, he was at UC Santa Barbara, we organized a workshop to bring together folks from industry and academia who were building tools for spatial analysis. And this was in the very early days of open source. In fact, there were heated debates at this meeting about the relevance of open source to GI science. And I remember those vividly, even though it was a long time ago. But out of this meeting, Luke and I became convinced that we needed to run with this. We think it's going to take off. So at that time, in 2002, Luke had a package for spatial econometrics that has turned into a thing called GeoPandas, which is widely used in the social sciences. And I had a package called STARS to deal with the dynamics of convergence. Our goal was, at that time, there was pretty much nothing in Python for spatial social sciences. There was no way to read a shapefile. GeoPandas wasn't around yet, Shapely wasn't around yet, so it was starting from ground zero. So we said, well, we want to work on the analytics, but in order to do the analytics, you need to be able to process and harmonize and project the data. So we had to write our own technologies. Jump forward to today, we're replacing all that with more performant code. And the goal was to build a library that others could use in a variety of mechanisms, be it at the shell, which is the typical work case for a scientist, or build toolkits for, in our case, ArcGIS and QGIS, or web services. So this is where it began for me. This was a project I had from a different NSF project where I built this interactive visualization system where you could interrogate the map, do brushing, and it would update the regressions for the scatter plot. You could look at where you are in the distribution, and it would highlight on the map. And this was all done with TickleTK. And someone in my group, I had a fellowship, said, you should really check out Python. And that's how I got introduced to Python, just a colleague mentioned it. So this is how I got introduced to our community. And I talked to Fernando yesterday about this, but at 2003, which was the second ever SciPy, I went to go, and I took a bunch of my students, and this changed my life, this meeting. it was a breath of fresh air to go to a meeting where people were genuinely interested and fired up about what you were doing. I was the token social scientist at this meeting, but people like Fernando and Prabhu were incredibly welcoming, and I was blown away because it was very different from my typical academic experience at a GI science conference where it's a little more dog-eat-dog kind of thing, and I thought, this is fantastic. So thanks to the Wayback Machine for showing me this. So a little bit about PySAL. It's a federation of packages organized into 4 layers. So there's core libs for data processing I/O. There's an exploratory module that has a bunch of individual packages for different types of exploratory spatial data analysis. For confirmatory modeling, there's a layer there, and then there's a visualization layer. So at the core lib, we have built-in examples to get people running. But the core time we've spent is on spatial weights and spatial graphs, because these are central to a lot of spatial analytical tasks, whether you're trying to measure dependence in space, or whether you're trying to do some type of clustering problem where you want to build regions that are spatially contained or spatially constrained. And so these graphs, we've spent a huge amount of time in trying to optimize these and make them scalable. For exploratory data analysis, where you're trying to generate ideas, identify patterns, and maybe lead to confirmatory analysis, there's a lot of different aspects to that in spatial analysis. So ESDA, exploratory spatial data analysis, so you can think about EDA, but where space is central to the question. So we'll see some illustrations of that later on, testing for global autocorrelation, and then hotspots and cold spots. Giddy came out of the STARS project trying to model the evolution of the maps over time, but also the distributions as well. We have a module for inequality, spatially explicit inequality measures. So typically people use things like Gini coefficients, but those are aspatial. We've done a lot of work trying to introduce spatially explicit inequality measures. MomoPy is a package for spatial syntax and studying spatial street structure of cities for comparative urbanization kind of studies. There's a point patterns module for folks dealing with point patterns. The segregation model came out of the Ritter grant. And then for certain types of phenomena in the social sciences, it's network constrained. So certain types of crimes, accidents are constrained to being on the network, and that's a different type of analysis than dealing with planar space. So that's the explore layer, and those are 7 packages. The model layer, again, there's 8 here. So access is a module that implements common measures that are used to measure access to resources. So in the epidemiology literature, there's a huge amount of interest in trying to come up with measures of disparities, access to, say, health resources, and access is the module that does that. MGWR is a multiscalar geographically rated regression, where you're allowing the parameters to vary in space in your models. There's a GLM module. SPINT is for spatial interaction data, where you have, say, migration data or trade flow data or conflict data between places, and you want to model those interactions. Gravity and interaction models are there. SP-opt is an optimization package, and there's 2 parts to that. There's the regionalization and clustering part, which is used to, say, define neighborhoods in space. But then there's also location allocation modelings and optimization models and routing literature, routing algorithms implemented in OPT. SPReg is my colleague Luke Anslin's spatial econometrics package that's widely used in the spatial sciences, social sciences. And there's a variance component module. And then Tobler is spatial interpolation module, where you typically say you're interested in yesterday's vote. The voting data is typically recorded at precincts, but you don't have socioeconomic attributes for the folks who voted. So a lot of the literature interpolates from, say, census tracts or whatnot. Tobler allows for those kinds of change of support problems. And then the visualization layer, MapClassify is heavily used by GeoPandas to do choropleth maps. So it implements about 18 or 19 different classification schemes. We'll see some of those today. And then SPLAT is a wrapper where we wanted to have all the common API interface for visualization of all those modules. So all of these packages can be installed individually if you want them. And we learned from the Jupyter project, we also have a meta package. So if you just conda install PySAL, you get everything. Or you could say conda install MapClassify and just get MapClassify. All right, so this is a typical workflow for say, an economist or a sociologist studying with spatial data. So first they want to represent spatial context. That's done with the graph or the spatial weights. Then they want to explore their data and test for spatial dependence. That's done with some of the ESDA module, things like global Moran's eye, and then local versions to detect cold and hot spots. The goal there is to uncover patterns. And then at the confirmatory level, you would either have theory that tells you you want to test this model. There's a lot of that in the social sciences. And then the goal there is to have an improved model that takes space into account. So let's look at a simple example, looking at that income data we started with for the counties. The goal is to identify where high values cluster in space with low values, and these are so-called hot spots and cold spots, right? High, high, and low, low. So you have to load the data sets, you gotta define neighbors with the graph, you gotta calculate the statistic, and then you wanna visualize it. So on the right is the code, and subject to the imports, you get to your result with 5 lines. Okay. Now I'm old enough to remember trying to do something like this in the old pre-Python days in ArcGIS, and then going to something like Gauss where you would write the code. It was very painful. That was an awkward workflow. So this community has fundamentally changed my workflow for sure. So what do you get out of that? That's the spatial graph. So the spatial graph deals with contiguity relationships. Here we're using Queen on an irregular lattice. So if 2 polygons share a vertex, they're neighbors. Now you might think that's a simple problem. Turns out it's not, because the data is typically lousy. There's all kinds of encoding errors for the polygons, and this is often overlooked in the literature because sociologists who care about segregation don't really spend time thinking about whether the spatial data is accurate or not. But very often there's problems. So you miss contiguities, and then you miss a neighbor relationship, and then your measure of dependence is going to be biased. So we spend time fixing that. This is what you get at the end of those 5 lines. So on the left here, this is the Moran scatter plot. So the attribute interest, we're looking at per capita incomes for the, median family incomes. On the right is where, say, the New York Times would stop. They would show you the map in wonderful D3 colors and then write a story about it. But maps can be really powerful, but maybe too powerful, because our brains are good pattern recognizers, and we can detect patterns that actually might not be there, particularly when you have these complex polygons. So we want to couple the visualization with the analytics and go back to the left. So the x-axis here is standardized. So counties to the right are high-income counties. Counties to the left are low-income counties. The y-axis, those are the neighbors of those counties, the neighbors according to the Rook graph that we saw before. So you have 4 quadrants. Upper right, those are places that are high income but surrounded by high incomes. Now it's just not whether your neighbors are high, but how high. What is the local spatial association there? So there's inference underneath this, and we signify which ones are significant using essentially conditional permutation. So the red ones are the hotspots. Those are high-income counties surrounded by high-income counties in a non-random fashion, right? Cold spots, concentrated poverty, are the blue spots. And then you have spatial outliers. You have the high next to low, which are the orange dots, and then low next to high, which are the light blue dots. And you do have some of those. Okay, so that's a quick view of that. Now here's going back to some of the projects, eating our own dog food using this. This is a project funded by the Bill and Melinda Gates Foundation, who are interested in looking at disparities in public school outcomes in the US. So we had just finished the NSF project defining methodologies to define neighborhoods in space-time context, because neighborhoods in the social sciences are often assumed to be a census tract. Okay, and there's a debate in the literature. Some people say that's too big. Some people say that's too small. On average, maybe. But the census tries to draw the boundaries to have about 4,000 people every census. And when I was at Phoenix in 1990, what held 4,000 people in 1990 now held 12,000 people in 2000. So the census will change the boundaries. So you have splits and merges and whatnot, okay? So you have to deal with that, and that's what that project was about. So this is an illustration of trying to understand the school-neighborhood nexus. So what's the impact of, say, neighborhood poverty or violence on a kid's performance at school? But there's a smaller literature looking at what's the impact of schools on neighborhood dynamics. Okay, if you have children, you know this is a major decision where you locate was the case for me. And actually that red polygon is the catchment for where my kids went to school. And now my granddaughter's going there. That's Lemon Avenue, the red polygon. And in the US, about 70% of the kids in our country go to their geographically defined school. So that's changing over time, but it's still the lion's share of kids. The color polygons are geodemographic neighborhoods that are defined using this SPOP module to define the neighborhoods. And you'll see that there's a disconnect in the sense that the catchment's not commensurate with one polygon or one neighborhood. So they're not the same thing. They're not a one-to-one correspondence. And so with Gates, we try to develop an infrastructure where we could leverage this to come up with a more comprehensive understanding of the spatial structure of these important contexts. And then extend the idea of the local Moran plot to a bivariate case, where here we're looking at the public school catchments in San Diego County, where we are. And on the x-axis, we're looking at the scores for the schools. So anything to the right is a high-performing school. Anything to the left is a low-performing school. The y-axis is a measure of the level of parental education in the neighborhoods that are sending their kids to that school. And that's spatially explicit. So what do we see here? Well, level of parental education is a proxy also for levels of income. So we have hot spots where we have high-performing schools in areas of concentrated advantage. That's not a shocker. They stand out. And you also have areas of concentrated disadvantage where the schools are challenging. They're facing many more challenges. But the interesting thing here, and this is where spatial analytics reveal things that you didn't know beforehand, and this is what Gates was fired up about, were the outliers. So if you look at the quadrant on the bottom right, you have these orange dots. These are schools that they're in areas of concentrated disadvantage, but the schools are performing above average. So Gates is now taking this across the country and trying to see where those schools are and going in and learning from their experiences, because they're able to escape this poverty trap idea. There's also the underperformers, the light blue in the upper left quadrant. Those are places where there's resource richness, but the schools are performing below average. Gates didn't seem too concerned about them. Arguably so. A second project is with the National Institutes of Health to look at the spatial structure of the opioid epidemic with a focus on Riverside County. So that's the county. This is in collaboration with the anthropologist who does ethnography work with the communities impacted by this epidemic. So Jennifer Syverson, my colleague, would go in and interview the folks about their usage patterns. Why do they use in certain areas? And our part of the project is to develop spatial analytics to try and model that from two perspectives. One, trying to predict where fatal ODs may happen. But the longer goal, and we're in phase 2 of this, is then to use that to do spatial optimization for harm reduction services. If you're going to locate, say, a needle exchange program, which you can in Riverside, you don't have many resources. Where do you put it given what we know from the insights gathered through the ethnography work? So it's a fascinating project to be part of, incredibly depressing, but I think an important one. So that's just some of my work. We had, in writing proposals to NSF, this is from about 2020, we did a review paper of the uses of PySAL, and it was very eye-opening because usually your head's down trying to get out the next thing because you have a long list of to-dos. But it's used widely. It's used way beyond what I think Luke and I, when we started, never thought it would get this far, from criminology, economics, planning, religious studies, biology, technology forecasting, info visualization, ecology, and sociology, among many others. So, takeaway for the Jupyter communities, 3 things. Spatial effects, unlike many of my social science colleagues, they view it as a noise, something you want to correct for. You shouldn't think it that way because there's usually substantive information in the spatial effects, so you want to incorporate that. Number 2, they're the rule, not the exception, so you should always carry out diagnostics before getting onto the confirmatory modeling section. And then tools like PySAL make it easy to do this, so we don't have an excuse any longer to ignore space. We used to have an excuse because there weren't tools, but now there are. We have some resources. So there's a book 2 years ago we did using Jupyter Book 1. Geographic Data Science with Python. That's also available online. Danny and Levi and I are still friends, even though it was a painful process at the end for the publisher to get it into LaTeX form. But we still talk to each other. Recent book on the Handbook of Spatial Analysis in the Social Sciences, if you're interested in learning more about how that side of the world uses spatial analysis, and then a book with Luke on spatial econometrics. We have a large team, so there's 18 core developers. Most of these were students who came through one of these universities and then went on to become a professor all over the world. So we have people from the UK, Bristol and Liverpool, China, South America, all over. And it's a joy to work with this kind of team. It's just been something I feel very privileged to be part of. I want to thank NSF. We're in the middle of a POSE2 grant to try and foster an open source ecosystem for spatial data sciences. PySAL is one node in that ecosystem, and it's clear from just being here for 2 days that there's so many other nodes to plug into, and I think the future is incredibly bright for things in the Python world. And I also want to thank this community. I mean, that meeting in 2003 changed my life. I mean, it made me much more productive, for sure, but it also opened my eyes to how we do science in a more progressive and more welcoming way. And that's been something I try to instill in all my students. So I want to thank this community for all those innovations, not just the tools, but how we do things. It matters quite a bit. And then I want to express my personal thanks. 2 years ago, I was honored, and this is not a humble brag, to get inducted as a fellow to the AAAS. And what I'm most proud about is in the induction, they cited the contributions in open source through PySAL into the social sciences. So to me, that made a mark that what this community has done has been, and I'm just from one area, has impacted and revolutionized the way people do science. So I want to thank you for that. So I'll leave it there. Happy to talk if folks have questions afterwards. There we go.